going to be a brief video on rational exponents, specifically powers of radicals. And when I say powers of radicals, I really mean powers that will undo radicals. So in other words, if somebody gave you like the third root of x, well, I want to show you that raising that to the third power will actually equal x. And in fact, this is really the theorem for the entire video here. But let's just go back and talk about the fact that we have some prerequisites here. You're going to need to know what an exponent is. You need to know all about exponents, laws of exponents, integers exponents, and all about rational exponents as well. Let me start with a theorem. And this theorem can be somewhat confusing if you're not careful. It turns out, okay, if you have the nth root of some number and you raise that to the nth power, that will actually turn back into the number. So the nth root of b raised to the nth power is just b. And a lot of students think of this as, oh, the nth power will undo an nth root. And it is actually true as long as the nth root of b exists. And this is a very important point to make because a lot of people kind of skip past this, but this is very important to pay attention to. The fact is, if I were to give you, for example, the fourth root of 16 and we raise that to the fourth power. Well, if you do a little bit of the math here, the fourth root of 16 is just 2. And 2 to the fourth power is 16. So you notice that it does kind of work out in this case that the fourth root of b to the fourth power is actually just going to be that number, the radicand. So that does work out. But be very, very careful, because if I asked you what the fourth root of negative 16 to the fourth power is, well, that does not equal a negative 16. And in fact, it doesn't really equal anything, because we can't take the fourth root of a negative 16. The fourth root of a negative 16 for us right now does not exist. So that's a very dangerous assumption. You just can't do it. So it's one of these moments where you have to kind of say, well, can I take the fourth root of a negative 16? No, I can't. So this is not going to be negative 16. So let me just put this in here. This is not equal to a negative 16. Now, there are going to be some arguments from people about the fact that this might be a negative 16, but I'm just going to let you know that you have to pay attention to this as long as the nth root of b exists business, because when you solve equations, this is what's going to really determine whether our equation has a real solution. And so it's extremely important that you pay attention to that. So let's start with a simple example. We have the third root of 18 all being raised to the third power. By that theorem, as long as we know that we could take the third root of 18, which we know we can, this is going to turn into 18. The power and the root undo each other. But again, that was because I know that the third root of 18 is some real number. So that's extremely important to pay attention to. And of course, this can be used in some compound expressions here. So something like this, where we have a lot of factors being multiplied together. We could use the laws of exponents here to rewrite this. We have the product of negative x squared and the sixth root of x to the 17th, all being raised to the sixth power. So that's like saying I have a negative x squared being raised to the sixth power times the sixth root of x to the 17th raised to the sixth power. And so in that first factor here, I know that a negative raised to the sixth power is going to be positive. Negatives raised to even powers always turn out to be positive. So that negative is going to disappear, and I'll have x to the 12th right there. In the second factor, I know I could probably take the sixth root of x to the 17th. So I'm going to go ahead and say that the sixth power of the sixth root will cancel, and I'll get x to the 17th. Now again, that's assuming that we could do this, because if x is, let's say, negative to begin with, well, negative some negative number raised to the 17th power is still going to be negative, and you can't take the 6th root of a negative number. So this is just a warning that you must be extremely cautious when you do this. You have to assume that x is positive for this to happen. And by the way, you'll begin to notice that really where you start to be kind of concerned is when your powers and your roots are even numbers. Okay, so we're going to assume that x is positive, and when I multiply these two bases together, I'll get x to the, let's see, 29th power. So perhaps I should summarize kind of how this looks. I know that I'm not really big on summarizing that, but I probably should summarize this. So let me put this in a theorem again, and this time I'll write cases. So the nth root of some number raised to the nth power is equal to that number, as long as the number is positive or 0. But what if the number isn't positive or isn't 0? In other words, if that number is less than 0, well, then you got a couple situations. If n is odd, in other words, we're taking an odd root, like a third root, and raising it to the third power, well, it turns out that the nth root of that number raised to the nth power is still going to equal that number. The reason why is because you can take, let's say, the third root of a negative 27 and raise it to the third power. You can take the third root of a negative number. That's perfectly fine. So it turns out that's fair game. This will actually turn into a negative 27. That's totally fine. But if n is even, then you've got issues. If n is even, then the nth root of b raised to the nth power is not real. It's not a real number. So in other words, let's say the second root of a negative 4 raised to the second power, that's just not real. It's not a real number. So that's just to let you know that those are the conditions. As long as your base on the inside is, or your radicand I should say, as long as that's positive, it's fair game. They kind of undo each other. Or if your index and your power are both odd in the same number, then they undo each other. But if the inside of the radicand, or if the radicand itself is negative and the powers are even, you're pretty much done for. Okay, so that's what I was trying to get to. I'd like to do one last example here before I go, just to really bring home this idea. In this first example, I see we have 2 times 12 to the 1/3 power raised to the third power. Now remember, the 1/3 power is the cube root. So this is going to be 2 to the third power times 12 to the 1/3 power raised to the third power, or in other words, the cube root of 12 raised to the third power. Sometimes it's good to write that as the cube root, just so you could see that that's what it is. Cube root of 12 raised to the third power. Since the index and the power are both the same and they're odd, these will undo each other. So this is just going to be 8 times 12, or in other words, what is that, 80, 96? 96. By the way, you could have easily seen this right here, that these powers to powers multiply, right? So this would have actually been 12 to the first power. That's a great way to see it, but you do have to be very careful because of this situation down here. Again, I'm going to use the laws of exponents to say that's 2 to the 4th times a negative 12 to the 1/4, all being raised to the 4th power. Now, if you follow this idea here where powers to powers multiply, you're going to say that's negative 12 to the 1st, but you're not paying attention to something here if you do that. What you need to pay attention to is that 4 in the denominator means you're taking the 4th root. In other words, this is supposed to be the 4th root of negative 12 being raised to the 4th power. In the 4th root of negative 12, well, first of all, notice the index and the power are both even and the same, which means that I really hope this index or the radicand is non-negative, but unfortunately it's negative. The fourth root of a negative number is not real, so this answer is not real. Got to be very, very careful of that. Okay, so that's all I really wanted to say with this. That you just have to be very careful when you're doing problems like this. Okay, and maybe actually I just thought of one last example before I go. Let's take a look at something like this. Quantity negative a to the third power times the, let's do the fourth root of a squared, all being raised to the fourth power. Well, that's like a negative a cubed being raised to the fourth power times the fourth root of a squared being raised to the fourth power. The first part's not so bad, right? A negative number raised to the fourth power is going to turn positive. A cubed to the fourth power is going to be a to the 12th. Okay, great. The second part's kind of weird. First of all, the index on the radical and the power that we're raising it to are the same, and they're even. So we really hope that the inside is positive. Well, the inside will be definitely positive here because that's a squared. A squared is always positive. So this is just to let you know that if you have some guarantee that the radicand is going to be positive, then you can go ahead and do this cancellation process. And I happen to know a squared is always going to be positive, so the fourth power of the fourth root will cancel and leave us with just a pretty little a squared, and this will be a to the 14th in the end. But be very aware of that you must, somebody either has to tell you that your variables represent positive numbers, or they have to force your variables to be positive by squaring them on the inside or something like that. Okay, so be extremely aware of that.